Hi everyone. First of all, I just wanted to thank everybody for all of your feedback for today. As you can see, there's at least 70 feedback cards here, so I can't possibly answer everybody's questions. So I've kind of gone through and I've sort of summarized what I thought were the key topics that were confusing to people. And then I have a handful of other questions that I just wanted to answer in some specific questions. So it seemed like there were a few questions about, how you can predict whether a process is endo or exothermic. How do you explain the size or the magnitude, size and the sign of the enthalpy change, delta H? How do you predict intermolecular forces? What are some of the different, why are some intermolecular forces incompatible? Why is delta H of mixing negative? Why, so on and so forth. So I thought it would be good to kind of give people like basically a crash course, really, really fast crash course to explain the relationship between energy and forces. So this is my quick, rough, and dirty tutorial on energy and forces, so there's that. So very, very generally, they are related to each other. Energy and forces, they're related to each other, and one of the mathematically, this may be instructive for people who've taken calculus. If you haven't taken calculus, don't worry, I will still explain this without it. But generally, the force that something experiences is related to the derivative d by dx or d by dr. If you're talking about the radial distance, it's the slope of the potential, and I'll just say E potential, of the potential energy. So this is not a discussion about what energy and forces are, but that is how they are related. So I'll give you a specific example here. Since we're chemists, we deal with electrical charges, we deal with the electrostatic charge, the electrostatic force. So that's the Coulomb force. So mathematically, the Coulomb force is proportional to the magnitude of one charge, the magnitude of a second charge, and the distance between them. So if you have two charged species, I will call them Q1 and Q2. Let me get rid of that. So these are my two charges. They might be a certain distance away from each other. So I will call them, this is their distance. And their potential energy, their energy is proportional similarly to the magnitude of their charges, Q1 and Q2, and the distance between them. So if I wanted to sort of describe or explain, how does the energy of this system of particles change as I bring them together, or separate them, I can plot that out. So I'm going to show you guys a quick plot here of the energy as a function of r, of the distance. So this is going to plot out the energy on my x and on my y-axis. On my x-axis, this represents the distance between the two of them. And basically, if I'm going to plot out energy as a function of r, there's basically two different shapes that it can have. It could either look like this. So this is the 1 over r term here. So we have that energy is proportional to 1 over r. Or it could actually look like that. It's going to be this if the charges are oppositely charged. So if one of them is positive and one of them is negative, I have a positive times a negative. That gets me a negative energy. So this is specifically if they're both, one is positive and one is negative. This is the distribution you'll have if they're both positive, then you should have a positive energy, or if they're both negative, then you should have a negative energy there as well. But since we're chemists were normally dealing with an attraction between oppositely charged particles, I'm going to fixate on this case, that this curve represents how the energy of two oppositely charged particles changes as you increase or decrease the distance between them. So let's try doing that. Let's say that this is my positively charged species, this is my negatively charged species, and let's say this is the initial distance between them, and then I take these two particles and I bring them closer to each other. So here's Q1, Q2, and now their distance has diminished to R final. So if I was going to try to plot that out here, my initial distance might be at some large distance, R initial. That doesn't show up, does it? That might be R initial, so at a long distance, versus R final. So if I follow this here, that means that this represents my final energy, and this point over here represents my initial energy. So the energy change, so this is my initial condition, this is my final condition. The energy change for this process, as I go from final to initial, that should be, well, it should be negative, because it's a drop in energy going from a relatively high energy down to a relatively low energy state. So generally, when you separate charged species, that's implicitly, or that's inherently going to be an energy raising operation. If I have two magnets, the magnets themselves are neutrally charged, but they have a positive end and a negative end. So if I was going to sketch out what does this magnet look like, these set of magnets look like this. So I have a positive end, a negative end, a positive end, and a negative end. So I'm going to be separating these oppositely charged ends. When I do that, I have to apply a force. I have to supply energy in order to do that. If I'm putting energy into it, their energy is increasing. They are starting in this low energy state, which is stable, and then I have to raise up their energy to separate them and take them to a higher distance. So basically, whenever you are breaking bonds, so if these were two oppositely charged species, like a sodium ion and a chloride ion, separating those two ions is an energy raising process, so that ends up being an endothermic process. Somebody was asking me also, why are endothermic processes, why do they feel cold, whatnot? What's really the distinction between an endothermic process and an exothermic process? They both involve a transfer of energy. Endothermic processes are ones where energy is transferred into the system, meaning the system's energy increases. In this case, energy of the system is the sodium and the chloride ions, so energy has to come from outside of them to supply that energy. So this is my system, their energy increases, so heat had to be transferred in to get that to occur. So again, breaking bonds, in this case we're breaking an ionic bond. That's inherently an endothermic process. So anytime you're breaking a bond or you're separating particles, generally that's an endothermic process. And it's exothermic when you bring them together, generally. Now, other interactions can occur. People were asking, trying to understand, why is it that when you solvate sodium chloride, that's an endothermic process. When you solvate lithium chloride, that's an exothermic process. And the reason is that you're not just separating those ions, you're not just separating them from each other, you're also bringing them closer to water molecules. So again, very basically here, I'm going to sort of recreate the sketch I made in class today. This might be your sodium and your chloride ions. They're all bound up together. Yeah, you need to supply energy to do that. You need to supply energy to do that. But then you bring them closer to water molecules, and when you mix them together, you're now bringing together two charged species. The water molecules, they have dipoles. They basically look like little magnets. The sodium ions that they have, and the chloride ions, they have full charges. So the positive end of the water is attracted to the chloride ions. The negative end of the water molecules are attracted to the sodium ions. So again, you're then bringing together charged species, more or less. So that ends up being an exothermic process. So this delta H of mixing is less than 0 when I bring them together. So then I had a couple questions about, okay, why is it that oil and water's heat of mixing is so unfavorable? How do you predict the sizes of delta H? Well, delta H is an enthalpy change. That's essentially the same as an energy change. Numerically, they're not exactly the same, but conceptually, they're the same. We think of enthalpy as being analogous to energy. So how do you predict this enthalpy changes, delta H changes? Delta H changes are going to be dependent, their size is going to be dependent on the strengths of the forces. So if you have stronger intermolecular forces, you're going to see much more drastic energy changes. So remember I said that the force, that should be equal to the derivative of the energy. So it's related to the slopes of the energy changes. Is that what I want to say? So yeah, point being that the energy change, the magnitude of the energy change is going to be proportional to the magnitude of the forces between the particles. If you have strong forces, strong intermolecular forces, a curve for particles that are experiencing strong intermolecular forces are going to look more like, maybe that's not the best example, but change the shape here just a little bit. That's a little bit better. So for both of these, this one would be a relatively weak force. This would be a relatively strong force of interaction, because the slope is a little bit steeper. A little bit. I didn't quite draw it as nicely as I could, but yeah, it's basically a little bit steeper in any particular point. So, for example, in this case, I'm going from about the same distance. Maybe I'll make this curve a little bit nicer. So it's not the best possible curve. Point being that this one sees a larger change in energy than this one, than this curve sees going from the same distance. Here they both start with about the same energy of interaction, but when you get them closer, this one experiences stronger forces, so its change in energy is going to be greater. This one, if you drop the line down here, that's the final energy change for something that's experiencing stronger forces. So basically, the stronger your intermolecular forces and the stronger your interactions, the larger changes in energy they'll experience as you bring them closer to each other. So then, here's a question. Why then do oil and water, why do they have incompatible forces? Why do they not mix together? Why is their enthalpy change of mixing so small? That was another question I had. What does it mean? What did you mean with the enthalpy of mixing for oil and water? Why was that so small? Well, the enthalpy change is related to the forces, and the forces are related to the charges on the particles. Water So this is water here. I got that backwards. Water has all of these electrons on one side. Oxygen is more electronegative, so you end up with a partial negative charge on one side and a partial positive charge on the other side. So you get dipole-dipole type interactions. Oils have essentially no charges. So you have these partial charges. So the magnitude of their interactions are going to be related to those charges. So you might have a charge here for water that's, it's not a full charge, it's a partial charge. So I'll say that it's about 0.5. The charge on the oil is negligible. It's nonpolar, it's neutrally charged, it's not an ion, so it has a charge of 0. So 0 times 0.5 would be 0. There is no attractive or repulsive force between oil and water. So they have no driving force to mix together. That's not an energy lowering process really at all. Negligibly small but energy lowering process. And conversely, to separate the oil particles from each other, you still need to overcome their London dispersion forces. So they do have intermolecular forces. They have London dispersion forces with each other, but they don't have any type of preferential interaction with water's dipole moments. So anyway, so this term is going to be really, really small. This term is going to be really, really large, and it's a step up in energy to separate oils. To separate the water, that's also going to be a step up in energy. And to bring them together, there's no force of interaction between them. So the delta H of mixing technically should be negative, but it's very, very small. So these are both the other two processes that you need to do to separate the water molecules and make space for the oil particles, to separate the oil particles from each other. Those are both large increases in energy because you're, again, overcoming intermolecular forces. Bringing them together is sort of trying to drive things back together. But there's essentially no force of interaction. So if I was going to draw the curve for it, it would look something like this. It's very, very flat. There's essentially no force between them. So you get relatively no energy change. So here's another question that people had. Why is it that the heat of solution for sodium chloride is positive, but the heat of solution for lithium chloride is negative? Short answer is it has to do with the size of lithium. Lithium is considerably smaller. A lithium ion is considerably smaller than a sodium ion. So when you bring the water molecules in towards the lithium, they can get much closer on average to the lithium. You're bringing them from far away and then you're bringing them in close. Lithium has a radius which is much, much smaller, so this might be for lithium's radius. Sodium has a much larger radius. So that might be for sodium plus. So if I try bringing water molecules in, if I'm trying to mix them together, the waters can get significantly closer to lithium, so they have a much more negative drop in energy for their mixing process, for the hydration process. Yeah, and that's sort of the hand-wavy explanation for why lithium's has an exothermic heat of mixing. Again, the idea is that there's multiple processes that occur when you form this solution. You're not just separating the ions in the ionic compounds, you also have to bring them in and interact with the water molecules. That separation process is always an endothermic process. Bringing them close with the water molecules is always an exothermic, energy lowering process. And whether the net change in energy, whether for the entire solution process, is positive or negative depends upon the sizes of these energy changes. So this is the chart I was trying to draw in class today. You have essentially two parts. So this might be two ions together, you need to spend energy, go up in energy to separate them. So now I have separated my ions, so that's the delta H of the solute particles. And then you need to have a second step where you bring them in and hydrate them with the water molecule. So that's the second step here. So that either can be a relatively small set of interactions and a relatively small heat of hydration. So that would be for sodium plus and chloride minus once you've made them aqueous. Or it could be a much more negative set of interactions or a much more favorable interaction with lithium plus and chloride minus. Those both being aqueous. So the point being that whether it is a net positive or a net negative is basically dependent upon the magnitude of these interactions and these interactions. If this is very, very large, it doesn't matter how negative the interaction is, it will still end up being positive, so on and so forth. So you need to consider both of them. Okay, let's see. A little confused. All right, I think I just answered that. I'd like to review why exothermic solution, an exothermic solution can still feel cold. I think there might be a little bit of confusion there. If something is exothermic, that means heat is leaving the system. That means it should feel warm. An endothermic process should feel cold. I think there was some confusion today, so I'll just reiterate. The question was specifically about does the solution feel warm or cold if it's an endothermic process. If it's endothermic, so heat is going into the system, the process. So let me try drawing this out. So this was the solution process we were looking at today, just a little picture here. So we're going from this configuration to this configuration where the sodium ions have been separated and the chloride ions, the different ions have been separated from each other. So we were looking at this reaction, sodium chlorine solid going to sodium plus aqueous and chloride aqueous. This is the reaction, and we argued that it ends up being an endothermic process. Heat is going into it. So it is referring not to the entire system, but to the entire beaker of water. The system in this case is the sodium. This is the system. In which case, so here's my system, and this is my system. And the idea is, okay, it's endothermic. We went through a long argument for why it's endothermic, and it's not made, again, not quite as simple of a problem as we'd like it to be, but it's an endothermic process, so it has to absorb heat. So where it's absorbing heat from is the surroundings, which in this case is the surrounding water. It could actually be absorbing some heat, like from like the tabletop or from the hot plate that it was on. Yeah, you could have some heat coming in from that point of view, but the part that's most intimately mixed and in thermal contact with our system, which the sodium chloride, is the surrounding water. So it actually absorbs heat from the water, which is why the solution ends up feeling cold. So little confusing, I admit that. I was confused about what reactions or mixtures are favorable and why. So generally speaking, anytime you have a negative delta H, if you have an exothermic process, that's favorable. And if you have a positive delta H, that's unfavorable. I say generally because there's lots of exceptions. We saw that today where we were mixing together sodium and chloride, we were dissolving sodium chloride, and that's a spontaneous process. It happened without us having to, supply any heat or heat it up. It happened spontaneously, so that was obviously a favorable process, but it's endothermic. So really, and this is a preview, really to decide whether a process is favorable or not is based upon the energy change of something we call Gibbs free energy. Now, what exactly Gibbs free energy is something that we'll get into in quite a bit more detail, but mathematically, Gibbs free energy is defined as the enthalpy change times temperature times the change in another term, which unfortunately is given the symbol S, but refers to something called entropy. If something has a positive Gibbs free energy, that we will say is non-spontaneous. And if something has a negative Gibbs free energy, we'll say that that's a spontaneous process. So generally, if you have a positive delta H, you're very likely to also have a positive delta G, and that will be non-spontaneous. If you have a negative delta H, you're also likely to have a negative delta G, and that will be spontaneous. But you can't say with 100% certainty because you need to factor in changes in entropy. And entropy is essentially a measure of disorder, how spread out and random and chaotic things are. And as we will learn, the second law of thermodynamics, the general observation of how the universe behaves is that things tend to become more disordered. And that really ends up being the driving factor for whether or not things are spontaneous or not. So you'll need to factor in both of those, and we will talk about, again, we'll talk about that in much more detail at some point in a few weeks. But for the time being, you can make an argument that if something has a very positive delta H, it's going to be unfavorable. If it has a small delta H that's positive, so the magnitude of the increase, if it's relatively small, it might be favorable. It just depends upon how large the entropy change is. Why are some substances more soluble than others? That's essentially, we kind of saw that today. Actually, sodium chloride is less soluble in water than lithium chloride is. And part of the reason why it's less soluble is that it has a positive delta H of mixing, a positive delta H of solution. Whereas lithium is exothermic, it has a negative delta H of mixing. So it's a more favorable process for lithium to dissolve than it is for sodium to dissolve. So you can talk about why some substances are more soluble in terms of their relative changes in energy. How can we tell if it's endothermic or exothermic just looking at the equation? Can we do that? Short answer, no. It's not going to be, you kind of can, but not just by looking at it. You have to use a little bit more insight to do it. If you look at the equation and you think about what's being expressed in the chemical equation, if upon deep analysis you determine that, okay, based on this chemical equation we have net bond breaking, I can predict that this should be an endothermic process. But even then, it's not always clear-cut. So I would say that no, you can't just look at the equation and predict whether it will be endo or exothermic. You need more information than that. Now, there are times when you can be supplied with that information, and then you can make a judgment one way or the other. But no, you can't just make that prediction a priori. Are dipole-dipole interactions the same as hydrogen bonds? No, they aren't. They are distinct. They are a specialized type of dipole-dipole interaction. They are a particularly strong type of dipole that occurs when you have hydrogen bound to any other highly electronegative element. And those highly electronegative elements are essentially nitrogen, oxygen, fluorine, and sometimes chlorine. So a dipole What do I want to do for this? I'll say sulfur. Sulfur is more electronegative than hydrogen, so you get a small dipole that points towards the sulfur. You have a partial positive charge on the hydrogen and a partial negative charge on the sulfur. Let me get a different marker here. So this has a dipole, and it will have dipole-dipole interactions with other molecules. Hydrogen bonds are when you have something that's even much more electronegative than oxygen, so you have a much larger dipole, and it's very much kind of, for lack of a better word, pointy. We'll often say that the dipole, the hydrogen, will tend to, it's nearly a full positive charge. So it will tend to interact with other negatively charged species very, very strongly. Less so dipole interactions. But yeah, basically it's a very, very strong dipole. That's a really oversimplification, but that's generally it. They are not the same thing, but they're very similar. Are we learning this as a review from last semester, or is this a continuation that will be discussed in more detail in this unit? Somewhat a review, because I'm aware that people are somewhat familiar, should be somewhat familiar with intermolecular forces, but really it's a chance to just get us talking about the terminology, get people used to thinking about this in the terminology, thinking about energy changes and how that relates to intermolecular forces, why some things are favorable or not favorable, things going up in energy, things going down in energy. So it's something that we will definitely be discussing in more detail, and we'll come back to it in some way in subsequent lectures. I was having problems identifying the types of intermolecular forces. So I don't have the time to address that at the moment because that's not a short discussion. I would say if you are looking to recap how to identify types of intermolecular forces, please see Chapter 11, which in your textbook, or come and see me during office hours. Chapter 11 deals with intermolecular forces. It also talks about other things like boiling points, melting points, liquids and solids. But that section 11.2 and 11.3 cover the different types of intermolecular forces and their relative magnitudes. And so what I would say is check through that. If you have questions, please come and see me. I will be very, very happy to discuss them either in office hours or just anytime I'm in my office. If I did not address, I don't want to make this video too long. We're at the half-hour mark now. If I haven't addressed any of your questions, please come by and I will be happy to answer them in person and probably do a much more effective job at that, where we can have a little bit of a dialogue about them. All right, folks, I will see you all on Friday. Have a good day.